Hi, welcome to the classes with Nadia. In today's class, we can discuss about the rates and orders of a process. Very commonly, a process like drug absorption or drug elimination may be described by rate by which the process proceeds. Rate is the speed of a reaction with which it occurs. The rate of a process may be defined in terms of its specific order, and the important orders of a reaction, especially in pharmacokinetics, are zero order and first order. Rate is the speed of a reaction with which it occurs. Okay, let's consider the reaction for better understanding. We can take drug X. Okay, drug X changed to drug M. In this reaction, rate of forward reaction is minus dx by dt. Negative sign indicates that concentration of drug X decreases with time t. At the same time, concentration of drug or metabolite or anything, the drug may undergo changes in body. So at the same time, concentration of drug M, say we can say M, increases as time goes on. So the reaction rate can also be expressed as dm by dt with no negative sign as the concentration of drug increases. Drug in form M increases. Okay. However, we do measure the decrease in concentration of drug X to determine rate of reaction. Okay, then assume C as the concentration of drug X, then the rate of decrease in C of the drug X as it is changed to M can be described by a general expression as a function of time. It is written as dc by dt equals minus kc raised to n. In this equation, k is the rate constant and n is the order of reaction. You need not be a mathematical genius to approach pharmacokinetics. Calculus is used in kinetic studies, but having an idea about mathematical expressions used in calculations is enough. Computer programs and scientific calculations are very commonly used nowadays. Okay, if n equals 0, it is a zero order reaction. If n equals 1, it is a first order reaction. So, order of a reaction is the manner in which concentration of drug influences the rate of a reaction. Okay, it's clear. So, order of a reaction is the manner in which the concentration of drug influences the rate of a reaction. Besides zero order and first order, mixed order also exists in physiologic system, but as I said, not important in kinetic studies. Then let's check zero order kinetics. In this equation we said above, if n equals 0, dc by dt equals minus k c raised to n becomes dc by dt equals minus k. K is the zero order rate constant. Upon integration of dc by dt equals minus k0 or dc equals minus k0 dt, we will get c equals c0 minus k0 t. C0 is the initial concentration of drug at time equals 0, and C is the concentration of drug yet to undergo reaction or the concentration of drug at time t. Here the thing is to be remembered is the rate of a zero order reaction is not influenced by the concentration of drug undergoing reaction. That is, the rate of reaction cannot be increased further by increasing the concentration of reactants. Okay, to understand it better, we can take the example of carrier-mediated transport of drug under saturated conditions. Saturated condition to be highlighted. Under this condition, the rate of drug transport remains constant as long as its concentration is in excess of saturating concentration. If even more drug is applied, it cannot enter into cell as the carrier is saturated with drug. So, concentration plays no role in such situation. Another example is constant rate IV infusion. You can imagine the situation in body when IV is um, given as an input in our blood. Okay, then we can move to zero order kinetic graph. It can be made by plotting concentration, that is dependent variable on y-axis, and time, that is independent variable on x-axis. This is the concentration time graph or zero order kinetic graph. In this graph, we will get a straight line for this zero order reactions and whose y-intercept is c0 and slope is minus k0. Okay. The time required to decrease C0 to C0 by 2 is known as T-half or half-life. In zero-order reaction, half-life can be determined as, let's see the equations. C0 by 2 equals C0 minus K0 into T-half. Then K0 into T-half equals 0.5 C0. T-half equals 0.5 C0 by K0. In zero-order reaction, T-half depends on the initial amount of drug, so it's not a constant. Okay, I hope it's clear for you, and be familiar with the equations. Final equations I have said in this topic. Then you can apply these equations at situations and practice or solve problems regarding this topic. Then it will be more clear to you. So in the next video we can discuss about first order kinetics. Thanks for watching. Bye.